be not competent about this. So we did the 10% yesterday. Did we finish the 10% discussion, or was I in the middle of it when the bell rang? Can you remember? So maybe we should kind of refresh that. But let's just refresh it. Okay, so I kind of divided this in half so that we could look at the two different sides. Okay, so we had found no evidence of a high mortality rate amongst baby birds in nests near cell towers based on alpha as 5%, which means we knew that our p-value was bigger than 5%, because bigger than 5% means we didn't reject the null. We didn't reject the null because we didn't find evidence of something going on. So back to the picture. At 10%, 0.10 alpha level, that almost looks like an alpha, we have a normal curve with some proportion that we don't really know p. And at the 5% alpha level, and I'm looking in the upper tail because I want to know if there's a higher mortality rate, so we only care about the top half. That's alpha equals 0.05. If that's the cutoff, anywhere to the right of that, I would reject the null. But since I didn't reject it, means technically somewhere down here is where p hat lives. So p hat is here, and I think I'd already drawn that part in, and that's kind of about where we lost track of time and the bell rang. I don't know where. P hat could be here, could be here, could be here, 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 anywhere to the right, to the left of that. So if I look at a new alpha level, so 10%, oh, that's going to write real well, isn't it? See, nothing there. New alpha level, so we hem in 10% of the area, alpha equals 10%. Then reject zone is now twice as big. So anything that lands out here, I'm going to reject the null. And I know that the p hat is somewhere to the left of the 5% marker. So if p hat is here, between these two cutoffs, if the p hat landed in there, then I would have changed my decision, and I would have rejected the null at 10%. But if p hat lies over here to the left of the 10% marker, which it might, then I would have a different decision. I would have the same decision and fail to reject. So with the information I have, it's somewhat inconclusive. If p hat had been here, I would change my decision. If p hat were here, I would keep the decision. So it could go either way. So I may make the same decision at 10%. But I can't be sure because I'm not sure where p hat is. So it's inconclusive. At 1%, it looks a little different. So on the other side of this little split the page here, let's look at 1%. So we start with the same scenario. We had some true, pretend that doesn't touch right there because I can't draw when I'm looking. Okay, I had some rate of mortality amongst baby birds, all baby birds. And at 5%, yeah, about there, alpha equals 0.05, I failed to reject. So that means p hat's over here, somewhere to the left. And then I change my cut score to alpha equals 1%. So instead of having 5% area out here in the tail, I'm going to go farther to the right where only 1% is above the cut. So I make a new line, a new threshold at 1%. And anything to the right of that, in that little bitty tail space there, anything to the right of that would be a rejection. Anything to the left of that is a fail to reject. Well, p hat is somewhere in here, which means it's also to the left of the 1% marker, which means p hat is not far enough out in the tail to reject, which means I'm going to keep the decision. So in this case, at 1%, the decision is the same, because the p hat is still to the left of the cutoff, so we're still closer to p than the reject zone. Okay, does that make some sense? Some of you could see that before I drew pictures, thinking about the discussion yesterday. Some of you need the pictures. If you need the pictures, then you should draw the pictures. Is it just me, or does that still seem really dark? That seems really dark. Let me try. I've got a magic button here, if I can find it. Is that any better? A little bit? Okay. Alright, so move on to the next slide. Here we go. What does it mean for a test to be statistically significant? Okay, so let's go back to your least favorite chapters that we studied on experimental design. Okay, so you don't have to draw this, I just want you to think about it. We spent some time talking about designing experiments or studies where we took a bunch of subjects. You don't have to write this down, just this is my thinking space. So we had some subjects, and I'm going to have to make them go this direction because I don't have room. And we split them into treatment groups. So let's say we gave this group of subjects if I can spell it right, treatment number 1. So maybe they got the old medication. And we gave this group of subjects treatment, I can't get that R in there for some reason, treatment number 2. And let's say that's a new medicine. And of course we randomly assigned treatments because we're good at running experiments. We control sources of variation that we can, and we randomly assign treatments to 2 different groups of people. Okay. And then after we gave them the medicine and gave it time to work, we compared results. So we might compare the percentage that recovered, the percentage that improved, whatever the case may be. Now, what we never dealt with back when we designed this study was how different do those results have to be before we can get funding to market the new medicine. And so that's where the inference part comes in. That's where the statistically significant idea comes in. Are the differences big enough between the treatment groups to claim that the new medicine is better than the old medicine? So we reject the hypothesis that they're the same, and then be able to get funding to market it. And that's what this statistically significant thing is. So statistically significant means that after you run the test, the p-value is smaller than the alpha level, so we reject the null. So statistically significant means something's going on, or at least we have the evidence to argue that it is. So if I'm arguing that the null is that the old medicine, the new medicine works the same percentage of the time as the old, and we got down here and we decided that the old was so much better than the new was so much better than the old that we had a p-value that was 0.003, definitely below any reasonable alpha level, then we would decide that we'd reject the hypothesis that the medicines are the same. There has indeed been an improvement, and so we have statistically significant results of our test, and that will get us some funding to get our medicine further researched and maybe marketed. Okay? So if you reject, you have statistically significant results. We saw that term back in those earlier chapters, but it didn't make sense what it really meant until we could quantify that, a way to actually crunch some numbers. All right, next page. We'll get these last 3 slides knocked out, and then we'll change gears. Okay, a little review. What is a critical value? That was a term from Chapter 18. The critical value is a fancy term for the Z-star that we used in a confidence interval. I can't spell today, in a confidence interval. So now that we've studied confidence intervals and we've studied hypothesis tests, it makes sense to kind of marry the two and see how they work together. So we pick a critical value to determine the level of confidence. If we pick a Z-star of 1.96, we're going to get a 95% confidence interval. Well, that has a connection to the alpha level of a test. So we want to see what that connection is. In order to see that, we're going to start with a excuse me. We're going to start with an actual scenario and compute a confidence interval. A little bit of review never hurts. So here we go. A confidence interval question. Soon after the euro was introduced as currency in Europe, it was widely reported that someone had spun a euro coin 250 times and had gotten 140 heads. That sounds like a p-hat. Let's see what that p-hat is. So p-hat, which is 140 out of 250. Let's see, if you multiply the top and bottom by 4, it'll change the percentage, so that's 56%. A nice round, not, ugly, long, non-repeating, non-terminating decimal. Not an ugly decimal. So 56% of the time we got heads. Do you think the coin's fair? I mean, what would they need to be fair? 50-50. You should get 50% heads, 50% tails. Now, could it be that it's 56% because we only spun it 250 times, and if we spun it more, we might get closer to 50-50? Maybe, because the law of large numbers says to settle down to the true probability, you really have to do a long time number of trials. But it also could indicate that 56%, because it's bigger than 50, it could also indicate that maybe it's not fair. Maybe heads lands up more often than others. So we're examining the fairness. To do so, instead of running a test this time, we're going to estimate the true proportion of heads using a 95% confidence interval. So we're going to do a confidence interval. What do we do first? Check conditions. Okay, check conditions. Check conditions. Okay, so they haven't changed. We have a random sample, independent or 10%, and the NP and Q conditions. Okay, we've practiced those a bunch. We should be real good at those. Is every spin of the coin a random event? Sure, because you don't know what side's going to land up when you spin it, so it's a random event. Is each spin independent of all other spins? Sure. Okay, so I'm going to do a great trick. I'm going to roll 2 conditions into one sentence. Okay? Yeah, I'm going to, because I've got limited space, I'm going to make it fit. So each coin spin is an independent random event. I am so good at this, I can put 2 in 1 this morning. Are you impressed? That took up less space than usual. You're all about that, right? Okay. How about that? So 2 done, 1 to go. Now the NP-NQ, it's kind of hard to skimp on that one because to get credit for it, you have to actually show it. So I'm going to squeeze that into the remaining space here because I'm real good at things that way. So NP, well, technically we don't have the true P. We think it ought to be 50%, but I'm not doing a hypothesis test, which means I'm not making a claim. I'm just examining a sample and making a prediction about the true P, which means I'm going to need to use the P hat here. You always use the P hat in a confidence interval because you don't know the true P. Okay? So that is, well, let's see, that's 250 times 56%, which is, isn't that the 140 heads we got? That's a count. Since it was given, I actually don't have to show the computation because I already know what the successes were. So that's an even better trick that I don't have to reinvent the wheel. I can just use what I already know. And that means in Q hat is the other 250 minus 140 is the other 110, the other 44%, which is 110 spins. Okay, so those are counts. They always are. And are those both bigger than 10? Oh, absolutely. So greater than or equal to 10, greater than or equal to 10. Ta-da! I checked 3 conditions in limited space. I feel confident that they are true. So what do I do now? Say what you're going to do. So maybe I'll move over to this space here. So we'll use a 1 proportion Z interval. Be careful that you don't say test there, because now that we have 2 procedures, it gets easier to get the wrong words in there. So you got to think, what am I making? I'm making an interval. I'm not running a test. Okay, mechanics, short and sweet. We have a formula. We stick numbers in the formula, and then we let the calculator finish it. So let's see. We start with P hat, which is nice and pretty percentage, 0.56. I think I'll roll with that because that's a little easier than 140 out of 250. And plus or minus, what's the Z star for 95%? 1.96. That one hopefully we just know by now because we use it so often. Multiplied by the standard error, and it's the standard error because I'm using p hats instead of the true p, and p hat's 0.56, q hat is 44.44, and the n is 250. So I would probably, because I want to do things quickly and efficiently, finish that on the calculator. So menu, statistics, confidence intervals, and number 5 is one prop z interval. And I'm real happy that they asked me for successes because that's 140 and I didn't have to compute it. They just gave it to me. Do not put a p hat in there. Definitely don't put a decimal because it will not like it. It will not take it. Out of not 150, 250. So the lower bound is 0.498. That's pretty darn close to 50%, isn't it? And the upper bound is 62.2% if you round. Alright, so lower bound is 0.498, upper bound is 0.622. So we are 95% confident that between 49.8% and 62.2% of all spins will land heads up. Yeah, and so anybody think that's maybe kind of inconclusive? Because, I mean, if you round 49.8 to 50, 50's right on the edge. And most of the intervals actually above 50, right? Okay. And this is an uncomfortable place for us to find ourselves because we don't like things that are inconclusive. We want hardcore, good, conclusive evidence. That's what we're looking for in statistics, and sometimes we just don't get it, and we got to deal with it. And one of the things that the AP gurus who score exams in sessions that I've gone to before tell me is make sure your students see questions that aren't real pretty answers. Because if they get on the AP test and they see messy answers, they get real freaked out because they think everything's supposed to be pretty. This is statistics. It's not supposed to be pretty. It's supposed to be realistic. And realistic sometimes can be uncomfortable. So, that brings us to this question. Last slide. Celebrate that I'm almost finished torturing you. Does this confidence interval provide evidence that the coin is unfair when spun? Well, on one hand, 50% is in the interval. So I'm going to think while I write. 50% is in the interval. So the coin may be fair. Don't ever write anything like you're real sure, because you're never, statistics means never saying you're certain. It may be. But man, it's right on the left end. I mean, it just barely caught 50%. If we had made the sample size any bigger, if we'd spun it, say, 500 times, then the standard error would have gotten smaller, and we would have missed it. It would actually probably have had a left end above 50%. Unless, of course, we tallied up less heads the next 250 spins. So maybe I'm going to additionally argue that, but 50% is on the left boundary. So the rate of heads may actually, it's a weasel word, we're not sure, may actually be higher than 50%. So I kind of argued both ways because it is inconclusive when 50% is right on the border. Does that make some sense that you can kind of argue it both ways? If it does, shake your head yes. If it doesn't, shake your head no. because I don't read minds, and y'all just look, sitting there looking at the board, trying to figure out, why my voice is disconnected from the board over there. Okay. This is the last part. What is the significance level of the test? What does that mean?
Alpha level.
Yeah, it's another name for alpha level. So we just got introduced to that yesterday. So it may not have stuck yet, so it's just throwing it back out there. Okay, here's the deal. I like to draw pictures because, pictures are, easier to explain things. Okay, if the coin is fair, then we'd be looking at like 50%, right? Is the center of the sampling distribution. Now, you don't have to draw a picture, but I just think it helps to reason through this. I did a 95% confidence interval, okay? And if I were testing a hypothesis, because it says significance level of the test, I didn't run a test. But what was I really testing if I had? If I were really running a test, which I didn't do, I would assume in my null hypothesis that it's fair. There's nothing interesting going on. So in my null hypothesis, I would say, I'm just going to make some notes over here. If I ran a test, the null would say the probability of heads is 50%. The proportion of heads is 50%. And then the argument would be that it's an unfair coin. If it's unfair, what do you know? It's not 50, which means it could be less than 50 or greater than 50, right? So if I ran a test on this same scenario, it would be a two-tailed test. Because lower than 50% would mean unfair. And above 50% would still mean unfair. And so what percentage is on the lower tail and the upper tail combined?
100%.
So you would reject if you found a p hat in either of those tails. What's the probability of finding a p hat in those tails? 5%. That's your alpha level. So that is your alpha level. The alpha level is your reject zone. And if the middle 95% is, this is what we think p actually is, then the outer 5% would be the rejecting area. In a two-tailed test, then it's always the sum of those two tails. In a one-tailed test, all that alpha would be on one end, so things would look a little bit different. We just need to see that connection between the confidence interval takes the middle part. The hypothesis test is looking to see anything in the outer, in the tails, but there's definitely a connection between the two. Does that make some sense? Well, each tail is 2.5. So if you have 2.5 down here, and you could reject if you're less than, and you have 2.5 up here, and you could reject if you're greater than, because it's a two-tailed test, if you got a really low percentage, like 30% heads, you would reject down here. If you got a really high percentage, like 60% heads, you'd reject up here. And since both of those would lead us to rejecting the null, then they both of those 2.5% go together to make a zone in which we would reject the null. And the total of the two areas is the 5%.
It's only 2.5,
Right.
so it's greater than.
When we do a p-value, if we run this test and we get a p-value, if it's a two-tailed test, so we've got to think about what that test looks like. When you do the normal CDF that says you have a proportion of z that's bigger than whatever that z-score is, we end up doubling it in a two-tailed test. So we take the 2.5% on this end and the 2.5% on this end, and they both are included in this is bad space. This is unusually far away from p. Have I answered the right question? I don't think I'm answering the right question. It's 2.5%. So so that's when things get kind of weird, and that's where we're going to start tomorrow's discussion. Is if it's a one-tailed test, then if it's 95% in the middle, then then you only have 2.5% on the upper tail, which means your alpha level doesn't connect to your confidence interval quite the same way as it does a two-tailed test. So you're on to something important there, and you're right. Yes, you're thinking right. Okay, how we doing? All right. So, I assigned yesterday the 1, 9, 11, and 13 from the day 1 homework. So go ahead and add 17 to it. I'm going to give you about 10 minutes to take a whack at number 17. If you're caught up, then you have plenty of time to do that one. If you're not caught up, then you're just behind and you can catch up on your own time because that's how it works. And then about 10 minutes from now, I'm going to pass out a reading that we need to do at least part of it together, because if we don't do it together, I can't be sure you're going to read it, and it's really important that we all need to read it. So take a few minutes, do some homework, do some practice, and then I'm going to give you some stuff and we'll kind of change directions a little bit. All right.
So the quiz is definitely going to be on Monday.